Hi guys, how are you? I hope you all are doing great. So today we'll be talking about denaturation of protein. Okay. In previous class we have completed the 4 structures of a particular protein like primary, secondary, tertiary and quaternary. Today we'll be talking about denaturation of protein. Okay. What is this denaturation all about? Have a look. Denaturation is basically the disruption. What is the meaning of disruption? Let's try to understand. You can also call it as destruction. Okay? Destruction of which structure? The quaternary structure of protein, tertiary structure of protein and secondary structure of protein. My dear friends, when you disrupt quaternary, tertiary and secondary structure of a protein molecule, okay, and that protein molecule is a native protein. Native protein basically means natural protein. You take one natural protein, correct, and you destroy its quaternary structure, tertiary structure and secondary structure. How will you destroy? You should know that you will destroy it by the application of change in pH. That means you have to change the pH of the solution in which you have kept the protein. And changing pH means you can have either acidic pH or basic pH. You can make it acidic or basic by changing the pH. So your pH can be here. You can have an acidic pH or you can have a basic pH. So this change in pH will destroy quaternary, tertiary and secondary structure of a natural protein. Not only that, but if you look here, the increase in temperature, if you increase the temperature, okay, of a solution in which protein is being kept, what will happen? This increase in temperature can also disrupt quaternary, tertiary and secondary structure of a natural protein. So once you have changed the pH of a solution, you have increased the temperature of a solution, okay, in which protein is being kept, what will happen to the protein? The natural protein, the native protein will lose its quaternary, tertiary and secondary structures. And because of the loss of those structures, what is going to happen? Have a look. It will result in the loss of biological activity of a protein. That means the protein will become now, its biological activity will become now what? It will disappear. So it cannot perform its biological activity now. Let us suppose you have an enzyme. Okay? Enzyme was catalyzing some reaction. You take an example of urease enzyme. It can convert urea into carbon dioxide and ammonia, correct? But if you expose urea to change in pH, like you put the urea in acidic, more acidic medium or more basic medium, okay? Or you heat the urea, that means you increase its temperature. Its structures like tertiary and secondary structures will be destroyed. And now the urease enzyme cannot convert the urea into carbon dioxide and ammonia. That means the urease enzyme has lost its what? Biological activity. Because it has lost its what? Tertiary and secondary structures. Due to what? Due to change in pH or increase in temperature. You take any protein. If you expose a protein to change in pH or increase in temperature, its quaternary, tertiary and secondary structures will be completely destroyed and then it cannot perform its biological activity. Okay, I hope everybody has understood. Let's take one example here. I am talking about the denaturation of lactalbumin. Please have a look here. The denaturation of lactalbumin. This lactalbumin is basically a milk protein. Okay, so this lactalbumin will be present in milk because it's a milk protein. So if you put some lemon juice when you are putting some lemon juice into the milk, that lemon juice is nothing but it's acid. That means you are changing the pH. So adding lemon juice means is a change in pH. And here the change in pH is basically you are making the pH what? Acidic. So you are making the solution acidic. Because lemon juice is acidic in nature. So change in pH is acidic only. So take a milk. Milk contains lactalbumin protein, which is a milk protein. Add few drops of lemon juice to it. When you add few drops of lemon juice to the milk, what you will get actually, you have to heat it. Heat this mixture. Take milk, add lemon juice, heat it up, you will be getting the cheese. And the formation of this cheese is nothing but it is the denaturation of lactalbumin protein. So lactalbumin protein which was present in the milk was denatured by two things. First thing is change in pH. Here change in pH. And second thing is by heat. Heat basically means increase in temperature. Increase in temperature. Two things you are doing, my dear friends. You are adding the lemon juice, that means you are increasing the acidic character. So pH will be less than 7 means acidic. So you are changing the pH. Second thing, you are heating the mixture. So that means you are increasing the temperature. So your milk will change into the cheese, and while the milk is converted into cheese, this lactalbumin will become what? It will get denatured. So that will be the denaturation of lactalbumin. It will lose its what? Tertiary and secondary structures, and it will become biologically inactive. I hope you have understood the process called as denaturation, my dear friends. So my dear friends, now we'll be talking about the renaturation of protein. This renaturation basically means inverse of denaturation. In denaturation, you are destroying the quaternary, tertiary and secondary structure of a protein. But in renaturation, you will be reforming again the secondary, tertiary and quaternary structure of a protein. So it's a reversal actually. If you look here, if we have a natural protein with us, natural protein. And for this natural protein, or we can also call it as a native protein. If I do its denaturation, how is denaturation done? Obviously, denaturation is done by these processes like change in pH, or you can do denaturation by increase in temperature. There are many other ways of doing denaturation of protein, means changing the solvent, like organic solvent you can change, okay? There are so many ways. But we have to focus on this change in pH and increase in temperature. So this natural protein called as native protein will turn out to be a denatured protein. So we are getting a denatured protein here, okay? Now, can we reverse this process? For every protein, we cannot reverse this process. In case of, eggs, if you just boil the egg and all, okay, the denaturation of protein which is present in the egg will happen. And you cannot renature it. You cannot regain, back the protein present in the egg, okay. So for some of the, proteins, the denatured form can be again converted back into the natural protein form. So such process will be renaturation. But remember, renaturation is not for every protein, it's only for some specific proteins it can happen. Okay? So in renaturation, what you have to do, again, let us suppose change in pH I have done first of all. If the pH was acidic here you have to make the pH what? Basic. Like basic in the sense means if the pH was here, let us suppose if the normal pH was 7.5. And then you have made it acidic and you have taken it, let's suppose 6. Then again from 6 you have to go back to 7.5. Okay? In the same way, increase in temperature. Let us suppose the normal temperature was basically at the beginning 37 degrees Celsius. And you have changed it. Let's suppose normal temperature was 37 degrees Celsius. And you have changed it to 39 degrees Celsius, then denaturation has taken place. Okay. Let's suppose this was the normal pH 7.5 and you have changed it to 6, correct? And the temperature was 37 degrees Celsius and you have made it 39 degrees Celsius. So if you reverse the process, reverse process basically means in renaturation the pH should go back from 6 to 7.5. Okay, so reverse should happen here, like your pH should go back from 6 to 7.5. Okay, and the temperature should come down from 39 degrees Celsius to 37 degrees Celsius. So you are reversing the pH and you are reversing the temperature as well. So in this particular process, what was the change in pH? pH was changed from 7.5 to 6. Okay. Let us suppose temperature was changed from 37 degrees Celsius 39, means increase in temperature was there. And what was happening? Denaturation. If you want the renaturation, what should happen? The pH should come back to 7.5. So it's coming back to 7.5. And the temperature should go back to 37 degrees Celsius. So it is going back to 37 degrees Celsius. So the renaturation will happen. So you will be getting a natural protein back. So it is a reversible process, but it is not happening in every protein. Okay. So renaturation is only possible in some specific proteins. Please make note of this thing. So my dear friends, now we will be talking about enzymes. What are enzymes actually? If you look at enzymes, first of all you should understand that they are proteins. Correct? But what is their role actually? Enzymes are the biocatalysts. That means the enzymes are present in the living system. Like enzymes will be present in the living things like plants, animals, humans, insects, everywhere. Okay. What is the role of an enzyme? It can alter the rate of biochemical reactions. That means the chemical reactions taking place in living system like plants, animals, humans, whatever the chemical reactions are taking place in my body, okay, those reactions are catalyzed by enzymes. So enzymes do catalyze the biochemical reactions. Okay. But what is the term here, alter? Please try to understand the term alter. Can you folks hear, sir, at this point? Alter the rate of biochemical reactions. The meaning of this alter. Have a look. Alter basically means change. Okay. So it can change the rate of biochemical reaction. But now this change can be further of two types. It may relate to increase or it may relate to the decrease. That means this change has to be either increase or decrease. Increase in what? The rate of biochemical reaction, or decrease in rate of biochemical reaction. So enzymes in our body, they will alter the biochemical reactions. They will alter the rate of biochemical reactions. That means they will either speed up the reactions in our body or they will just decrease the speed of the chemical reactions in our body. So that means the enzymes can be either positive catalysts or they can be negative catalysts. If enzymes are positive catalysts, they will increase the rate of chemical reaction. But if they are negative catalysts, then they will decrease the rate of chemical reaction. And this increase and decrease is known as change, and that change is basically called as alter here. So enzymes can both increase and decrease the rate of biochemical reactions. I hope, my dear friends, everybody has understood. Please have a look here now. Chemically, if we look, our enzymes are basically the globular proteins. So globular proteins will make your enzymes, correct? So enzymes are globular proteins. Another point we have, some enzymes are associated with non-protein part. See here, if you have a globular protein, just a protein, globular protein, and it's acting as an enzyme, that's good, well and good. But sometimes a protein is associated with a non-protein part, okay, then it performs its biological activity. Let us suppose I am a protein, I want to be an enzyme. So for being an enzyme to perform my biological activity, sometimes I need a non-protein part. And that non-protein part which I need is known as cofactor. So remember, my dear friends, some proteins can change directly into enzymes and do the biochemical reactions. But some proteins need a non-protein part. That non-protein part should come and combine with the enzyme. Then only enzyme can perform its biological function, that is catalysis, correct? And that non-protein part which is required for an enzyme is known as cofactor. And remember, cofactor is not required for every enzyme. Some enzymes can perform their function even without cofactor. But there are some enzymes, they need cofactor to perform their catalytic activity. I hope you have understood. Please make note of this particular thing. So my dear friends, some enzymes can function on their own, okay, and catalyze the biochemical reactions. But there are some enzymes, okay, they cannot function by themselves. They need something to perform the biological function. And what is that something which is required by an enzyme to be biologically active? And that is known as cofactor. If your enzyme is inactive, and that inactive enzyme is known as apoenzyme. So it's inactive enzyme. In order to make this inactive enzyme active, and the active form of enzyme is known as haloenzyme, we need cofactor. If the cofactor combines with the apoenzyme, it will give me haloenzyme, and that is active. Okay? But which kind of cofactor is required for apoenzyme to make it active as a haloenzyme? So cofactors, this cofactor can be divided into two types. You can have a cofactor like inorganic ions. Okay? In inorganic ions, you will be having iron, magnesium, zinc, copper and cobalt ions. If you give this iron to the apoenzyme, iron is nothing but inorganic ion and it's nothing but cofactor. If you give this iron to apoenzyme, it will become haloenzyme. Okay? If you give cobalt to the apoenzyme, it will become haloenzyme. Correct? So it will become active. So it will perform its catalytic activity. Now, your cofactor can be also an organic molecule. Your cofactor can be also an organic molecule. Now, organic molecules can be of two types. Now, here the organic molecule can be coenzyme. Don't think that this is an enzyme. This is not an enzyme. This coenzyme is basically organic molecule. Please try to understand. This coenzyme is basically organic molecule, not an enzyme. If I give this coenzyme to apoenzyme, coenzyme is nothing but organic molecule, or it is a cofactor. If it is given to apoenzyme, if it attaches itself to apoenzyme, it will give me the haloenzyme, which is active. Correct? Now coenzymes are loosely bound to enzyme. So this coenzyme which I have, this coenzyme is a cofactor, and there is an attachment between cofactor and apoenzyme. Remember, this coenzyme is loosely bound to enzyme, and that loose attachment can be either through van der Waals forces or hydrogen bonds. Correct? That loose interaction. Now, what will be this coenzyme? Can you please focus here? What will be this coenzyme for you? It is loosely bound to your enzyme. Which enzyme? Apoenzyme, we can say. So I can also write down it's loosely bound to apoenzyme. Correct? After that, it is derived from the vitamins. That means these coenzymes can be derived from the vitamins like thiamine and riboflavin. So from thymine and riboflavin, we can derive the coenzymes, and those coenzymes are loosely bound to the apoenzyme. Okay, so there is a loose interaction between coenzyme and apoenzyme, and when they interact, okay, they form the haloenzyme. Now we have another one called as phosphatic group. It is nothing but it's again your organic molecule, or we can say it's again your cofactor. But here it is tightly bound to an enzyme. Which enzyme is tightly bound? It's tightly bound to an apoenzyme. And here this tight bonding or tight arrangement will be mainly because of covalent bonds. Here this loose arrangement or loose interaction between coenzyme and apoenzyme will be mainly through hydrogen bonds or van der Waals interaction. But here this tight bond between phosphatic group, which is a cofactor, with apoenzyme will be because of covalent bonds, and it is derived from the vitamins like biotin. So this phosphatic group is derived from the vitamins like biotin. I hope, my dear friends, you have understood. There are some enzymes, they don't need cofactors. They can perform their functions. So like I told you about globular proteins, correct? But there are some enzymes, they are inactive. They need cofactor to perform their function. So what can be your cofactor? Your cofactor can be a mineral ion, okay, or your cofactor can be a organic molecule. In organic molecule you can have two cofactors. One is coenzyme and another one is phosphatic group. So you take an apoenzyme, okay, then take a mineral ion, then they will combine to give us haloenzyme, which is active. Or you can take an apoenzyme, make it combine with phosphatic group, or make it combine with coenzyme, and then you will get the haloenzyme, which is a functional enzyme. Actually it will perform the catalytic activity. I hope you have gotten the idea. Please make note of this. So my dear friends, now we will be talking about few enzymes here, okay, and about their catalytic activity, what kind of catalytic activity they perform. If we talk about invertase, enzyme invertase, it will convert the sucrose, which is basically a disaccharide, into glucose and fructose. So here we are using an enzyme called as invertase, this enzyme you are using here. Maltose is basically a disaccharide, and it's converted into glucose and glucose, 2 units of glucose. It's also a disaccharide, and here you use an enzyme called as maltase. So you are using an enzyme maltase here. Then lactase enzyme is used to convert lactose. It's also a disaccharide. So you are using an enzyme lactase and converting it into glucose and galactose. Correct? Then you have an enzyme called as urease. This urease enzyme can be used to convert urea into ammonia and carbon dioxide. That is the role of urease. Then you have alpha amylase enzyme. Alpha amylase enzyme can convert your starch into N times glucose, because we know that this starch is basically a saccharide. So it has lots of sugar units in it. And what are those sugar units? Glucose only. So starch by alpha amylase can be converted into N times glucose, and this N can be more than 10. Okay? It can be 100 also, 300 also, 1000 also, but more than 10. Now if you look at this enzyme here, pepsin. Pepsin can basically convert your protein into smaller peptides. Protein, I told you, the N value in protein will be, N stands for amino acids, number of amino acids will be greater than 100. And here we are talking about smaller peptides. Smaller peptides can be your dipeptides, tripeptides, octapeptides containing 10 amino acids, 15 amino acids, 20 amino acids, 60 amino acids, but here the N value will be greater than 100, and here the N value has to be less than 100, okay, in case of smaller peptides, which means if the protein is broken into many fragments, Some fragments will have 10 amino acids, that is a peptide only, called as decapeptide. If some fragments will have 5 amino acids, we call it as pentapeptide. If it has 2 amino acids, we will call it as dipeptide. I hope you are understanding or not. So protein is converted into smaller peptides, and then these smaller peptides can be further converted into amino acids. You can further convert them into amino acids. So proteins to smaller peptides, and then smaller peptides can be converted into amino acids. If it is a decapeptide, for example, smaller peptides you have, let's suppose decapeptide, you can get 10 amino acids from decapeptide. If it is a dipeptide, you will get 2 amino acids. If it is octapeptide, you will get 8 amino acids. I hope my dear friends you have understood. There are so many enzymes and we will be dealing with them in this chapter, okay, at the right place. So please make note of these few enzymes here. So my dear friends, let's talk about now properties of enzymes. The first property is specificity, which means that an enzyme can catalyze only a particular reaction. Okay, urease enzyme, let's suppose if I have, it will only catalyze the reaction of like conversion of urea into carbon dioxide and ammonia. It will not catalyze any other reaction. So that means the catalytic property of an enzyme is specific. That's why I am saying the term specificity. Specificity is basically the property of an enzyme, which means an enzyme can catalyze only a specific reaction. One enzyme cannot catalyze all reactions. Okay, let me give an example for this. Have a look here. If I have basically urea with me and I am using an enzyme urease, yes, catalysis will happen. I will be getting carbon dioxide and ammonia. Carbon dioxide and ammonia I will be getting from urea. But if I have here in place of this urea, if I take N-methyl urea, if I take N-methyl urea and will use urease enzyme, okay, no reaction. Why? Because urease enzyme can only catalyze the conversion of urea into carbon dioxide and ammonia. The urease enzyme cannot catalyze the conversion of N-methyl urea into the products. So it means N-methyl urea, okay, cannot be catalyzed. This reaction cannot be catalyzed by urease. Urease will only catalyze this reaction. That means the property of an enzyme, that is specificity, that one enzyme can catalyze only a particular reaction, not all types of reactions. I hope you have understood. Let's take efficiency. How much efficient an enzyme can be. You know that enzyme can speed up the reaction. Which reaction? Biochemical reaction. Up to 10 raised power 20. It's a very huge amount. This will be the speed, given to a reaction by an enzyme. Up to 10 to the power 20 will be this. This is how much efficient, we can say that how much efficient an enzyme can be. That it can speed up your biochemical reaction to this large extent. It's not a small amount, 10 raised power 20. Okay? Now, let's look at the small quantity. So that's also the property of an enzyme, which is basically the small quantity. What's the meaning? Enzyme is required always in small quantity to catalyze a specific reaction. See here, when you want to catalyze any reaction, you don't need 1 kg of enzyme, 2 kgs of enzyme. You can use enzymes in micrograms or nanograms, and that small quantity of enzyme is capable of catalyzing a particular reaction. That means we don't require enzymes in large amount. The enzymes are required in very small amount to catalyze a reaction. That's why I wrote here that enzymes are always required in small quantity, not large quantity. Okay, so they are very efficient. They can catalyze the reactions even if small quantity of enzyme is being taken. Let's go for the optimum temperature and pH. When we look at the enzyme pepsin, it works at a very high acidic pH in the stomach, pepsin. which converts your proteins into the peptides basically. So there the pH is almost, between 1 to 2, okay? But usually the optimum pH is taken as 7 and the optimum temperature is taken as 37 degrees Celsius, okay? So optimum temperature and pH at which enzyme will act, the temperature is taken as 37 degrees Celsius, that is the optimum temperature for enzymatic function, and the pH taken as is nearly a neutral pH, that is 7. So in human body, if you find out that enzymatic activity in human bodies especially will take place at 37 degrees Celsius. The enzymatic activities are biochemical reactions catalyzed by enzymes take place in human body at 37 degrees Celsius. And most of the enzymes require pH of 7, optimum pH of 7. Some enzymes may require, less than 7, some requires little more than 7, but most of the enzymes require the optimum pH of 7 for their catalytic activity, okay? And finally we can have enzyme inhibitors. Enzyme inhibitors are basically the substances which will reduce the efficiency of an enzyme, okay, which will reduce the catalytic activity of an enzyme. So it means the inhibitors will decrease the catalytic activity or it will decrease the efficiency of an enzyme, okay. And what are those inhibitors? Your inhibitors can be the drugs. Basically the medicine which you take, they can act as inhibitors, and even the alcohol can also act as inhibitors. I hope, my dear friends, you have understood about the properties of enzymes. They have a specificity, they have the efficiency, they are required in small quantities, they work at optimum temperature of 37 degrees Celsius and optimum pH of 7, okay? And finally, enzyme inhibitors can decrease the catalytic properties or efficiency of an enzyme, and your enzyme inhibitors are drugs, or you can take an alcohol right out there. Please make note of this. So my dear friends, now we'll be talking about the mechanism of enzyme action. How does enzyme catalyze a particular biochemical reaction? We'll be looking into that. Before we look into that, I want to tell you something, that if you take your enzyme, okay, can you please focus at this point, sir? Entire this area, okay? Now, my dear friends, please look here. So make note of this first. If you have an enzyme, your enzyme can have one place first of all we'll talk about. It has a region called as active site. Your enzyme will have an active site, correct? So you have an enzyme, that enzyme has an active site. Then active site can be divided into two parts, okay? Your active site it contains two sites actually, this active site. One is binding site. Can you zoom it here? Okay. Another one is catalytic site. What is the role of this binding site? It will bind means it will attach itself to substrate. Who is your substrate? Means reactant. So it will attach itself to the substrate molecule. Substrate is nothing but your reactant, correct? What is the role of a catalytic site now? This was the role of binding site. Active site has two sites in it, binding site and catalytic site. Binding site, it will bind to substrate. Substrate is nothing but reactant. And your catalytic site, once the reactant or substrate molecule binds to the binding site, okay, of an enzyme, then the catalytic site of an enzyme will convert this reactant into product. So it converts substrate into product. Substrate means reactant. Substrate into products. Okay. Now, very easy it is. You have an enzyme. Enzyme has an active site. Active site has two regions. One is binding site and one is catalytic site. Binding site means that site which can attach itself to the substrate, means reactant. So binding site will attach itself to the reactant molecule or substrate molecule. Then the catalytic site will convert that reactant into the product. Correct? So let's have a look here about now mechanism of enzyme action. The specific action of an enzyme. Why we call it as specific action? In properties of enzyme, I told you that every enzyme will catalyze a specific reaction, a particular reaction. One enzyme cannot catalyze all reactions. It will catalyze only a particular reaction. Okay? Now we will be talking about here the specific action of an enzyme with a single substrate. Single substrate basically means here single reactant. So you will be taking a single reactant here. Correct? Can be explained using lock and key hypothesis. So how does an enzyme will catalyze a particular reaction with respect to a single substrate? It can be understood by lock and key hypothesis. This lock and key hypothesis was given by Fischer. Okay. So my dear friends, now we have one reactant called as one substrate. Enzyme will act on that substrate and will convert that substrate into products. So how does this action take place? Okay, it was explained by Fischer through lock and key hypothesis. So what is this lock and key hypothesis? Let us understand. Let's look from here. This is our enzyme, and this enzyme you can consider it as a lock. And this is our substrate. Substrate means basically the reactant. And this is considered to be the key. Correct? If we take this enzyme, an enzyme is a lock. And this substrate, we substrate here a single substrate. This is a key. You consider it as a key. So lock and key hypothesis, it is given by Fischer. Correct? Now, this site of an enzyme, I told you that enzyme can have an active site. Okay? You consider this site of an enzyme as active site. So enzyme has an active site. Correct? So enzyme is your lock and substrate is your key. Okay? So we have an enzyme here as a lock, substrate as a key. After some time, what will happen? The enzyme substrate will combine. This substrate will come. Who is the substrate? Reactant, or we can say key. Key will come down and fit into the active site of an enzyme. Now look here. This is your substrate, and it has fit into the active site of an enzyme. So substrate fits into the active site of an enzyme. This substrate fits into the active site of an enzyme. Now we are getting enzyme substrate complex. So this is my enzyme substrate complex. So it means key has entered into the lock. You consider this as lock, this as key, so it has entered into the lock. Okay. After that, what will happen? Can you see here the substrate molecule? Substrate molecule is here basically your reactant. And now see, it has broken here. That means something has happened to the substrate molecule. It has broken into some parts. You can see the cleavage here, it has broken. That means the substrate has changed basically into product. And product is still attached to an enzyme. Product is still attached to an enzyme. Okay, here the substrate was attached to an enzyme. Now substrate has been converted into products. And products are still attached to an enzyme, so we call it as enzyme product association. And remember, there is a weak bond. There is a weak bond between enzyme and product. Bond is very weak. So enzyme will easily leave this product now. But bond between substrate, the bond between this substrate and enzyme is very strong bond. When this substrate is converted into product by an enzyme, okay, then what happens? The enzyme and product bond is very weak. So this product can come out now. Okay. Once this product comes out, now you will see that you got two products here, this and this. Let's suppose this is A, this is B product. So two products you got here. And even the enzyme has also come out. Okay? So my dear friends, finally your substrate molecule is converted into the products finally. And look at the enzyme. Look at the enzyme at the beginning and look at the enzyme at the end. So during this process what happens? Enzyme remains unchanged. Enzyme remains unchanged. This is very much important. Enzyme remains unchanged during a biochemical or chemical reaction. So nothing happens to an enzyme in a chemical reaction. Let's consider it as biochemical reaction here. So I hope, my dear friends, you have understood. We took a substrate, consider it as a key, and enzyme as a lock. Enzyme will have an active site. This substrate will come and fit into this active site. Now we'll make enzyme substrate complex. The affinity between substrate and enzyme is very strong. Strong bond will be there. Okay. So after that, what happens? The substrate is converted into product. Can you see the cleavage here? It's converted into products. But product is still attached to the enzyme, so it's called as enzyme-product association. But bond between product and enzyme is very weak, so product will come out. Product comes out here, and enzyme also comes out. This enzyme has remained unchanged. There is no change in the enzyme. Okay, so we say that enzyme remains unchanged during a biochemical reaction. I hope you have understood this lock and key hypothesis given by the Emil Fischer. Please make note of this. So my dear friends, let's look at the applications of enzymes. Okay, so have a look here. For the production of beer and wine, okay, these things can be manufactured. Okay, beer and wine manufactured by fermentation of carbohydrates. So when we do the fermentation of carbohydrates, that fermentation happens, obviously it's an anaerobic respiration. We will be producing the beer and wine. Second point is that manufacturing of sweet syrup. Sweet syrup can be made from the corn sweet or corn, starch. And finally, the production of cheese is through the coagulation of milk, because previous time I told you basically that there is a lactalbumin protein present in the milk. When it undergoes denaturation, okay, you will be getting the cheese. And denaturation happens when we add on a few drops of the lemon juice into it. That means we are altering the pH of that particular process. So once again I am telling you this particular thing, application of an enzyme used for the beer and wine production through the fermentation of carbohydrates. You can also manufacture the sweet syrup, okay, from the corn starch. And finally, you can produce the cheese from the milk protein by the denaturation process. I hope everybody among you has understood this thing. May God bless you. Have a good time. Yo-yo.